The National Center for Quality Research, which is housed out of Heidelberg College. They do research throughout the state and beyond that. I think they got like 16 tributary monitoring stations here in the state of Ohio. And they've been doing some here at the Grand Lake St. Mary's, specifically the Coldwater, the Beaver, and also the Chickasaw. And we've asked them to come here today to give us an update on the results for the monitoring data that they currently have. So we would like to welcome Ken Krieger and Laura Johnson from Heidelberg. And Laura, I think you can will be presenting most of the information. So let's come up and show us what you got.
Thank you, Tim, for the invitation to come this morning. We had a choice of a couple different months to come during the summer, and we thought, well, you probably want to hear about what we're finding sooner rather than later. So we offered to come this morning. So we're glad to be able to come and be on the shores of this really beautiful lake out here. So Laura is going to do most of the presentation of the work that we are doing and the findings that we have. I wanted to show a few slides to start it. I also I brought a few handouts from our center. We do some biological studies as well as water chemistry studies, and I'm trained originally as a biologist, so I couldn't help but bring a few of our publications about biology too. And I've done a lot of work on mayflies up at Lake Erie over the years, and so I have a little handout on, is this a mayfly or a midge that's showing up here? And I see you have a lot of midges outside the door this morning. Well, I'm not here to talk about biology, so I will move on. But help yourself after the meeting to some of these handouts that we have. Also, we do have a website at heidelberg.edu, and we have annual reports right on the front page. You can click the link to those and find out about different programs. We also have a private well testing program. I think that's on the slide, so I'll just move on to the slides. Is that a portable slide?
Yes.
Okay, this will be great. Thank you. Okay, so we are located in Tiffin, Ohio, about 2 hours from here. The National Center for Water Quality Research has been around since about 1969, and the lab or the center is involved in a number of different programs, and our primary program, which is what we're going to be talking about today, is the Heidelberg Tributary Loading Program. And a lot of the data, actually, that we collect all the way back to 1975 is on one of the pages on our website. So if you're data-oriented, there will be plenty of that to look at. Some of our Grand Lake tributaries are also on that site. We also operate a cooperative private well testing program that has involved county agencies or state agencies in 26 different states in the country and all counties in Ohio. That's been going for about, well, since 1984, I believe it was. And so we've been involved with soil and water districts and county health departments and extension agencies in operating that program over the years for private well owners. You don't even have to work through those. You can submit well samples to us individually. We are supported entirely through grants, contracts, and contributions from the federal and state governments, as well as various foundations and some corporations. And we have a number of research grants, and we do these grants collaboratively with other universities and with agencies. So we're doing work right now with Ohio State University, University of Toledo, Ohio EPA, ODNR, University of Michigan, U.S. Geological Survey, USDA, and so on. So we're highly involved with other people because nowadays research does involve multiple disciplines to answer a lot of the complicated questions we have out in the environment. So no one person can certainly look at the whole picture very well. We also do contract work for other universities. We actually we're getting samples in, I think, even from Canada right now under contract. So we do the work that way. We also are involved, as you might imagine, in the curriculum in environmental sciences at Heidelberg University. Put in a little plug there to say that it's a relatively small program, which means the students, the undergraduates, get a lot of attention from us, more than they want sometimes. But we also have an excellent placement of our graduates in the environmental careers, such as water departments. The Ohio Northeast Ohio Regional Sewer District has hired a number of our people as biologists as well as chemists, and they do very well getting internships while in college and so on, and they do very well competing for graduate school. So I think we have an excellent program. You have to watch where I'm walking. All right. We do a lot of workshops and so on throughout the year, as well as meetings like this. We have 11 people on the staff, covering from modeling of water quality issues to the biology and the water chemistry I talked about. And so I think that covers that. This is a map showing the 16 stations that we currently are operating throughout the state of Ohio. You see that we are in the Ohio River Basin, on the Muskingum, Scioto, and Great Miami rivers, as well as Grand Lake St. Mary's, of course. And then we have our remaining stations up in the Lake Erie watershed. And indeed, it was the Lake Erie basin that gave us our start back in the 1960s and 70s with the issues going on with Lake Erie at that time. And this is a map showing our three watersheds, or at least the two watersheds going into Grand Lake St. Mary's. We started out with Chickasaw Creek. I believe it was the 1989 water year, so we started probably, I think, in October the 2009 water year. So it started collecting samples, I believe, in October of 2008, is that right? And then we added Coldwater Creek later, and now we are looking, as of last October, at the outfall from Grand Lake St. Mary's itself. This allows us to see what's coming into the lake, as well as then what's coming out, how much is being retained in the lake, and how the different nutrients are being transformed as they go through the lake. So we're very interested in that. In terms of the sponsors for this work, we were approached by outside agencies really to do the work initially. And we began with Chickasaw, as I said, in October 2008, and that was originally funded by the Natural Resources Conservation Service through October of 2011, at which time the state of Ohio, through a line item that we had in the state budget, funded the program for about 6 months there, and then following that, through the present time, the Ohio Water Development Authority has funded ODNR to pay us to do the monitoring. In other words, universities are not able to go to the Ohio Water Development Authority for their funding, so an agency does that. And so I'm showing that as through December 2015. Actually, I should have written through June 2015 because the state operates on a fiscal year basis that ends at the end of June. It gets complicated. The Ohio Water Development Authority operates on a calendar year, so I won't go into that too much. But we have 3 different calendars we work under to keep our funding straight. Coldwater Creek was added in October of 2012, and that's been funded by ODNR itself as opposed to OWDA. And then we added Beaver Creek back in April. We started getting daily samples beginning about October for that, and ODNR is also funding that through June of 2015. Actually, we have a 2-year agreement for that. So I'm being optimistic is what it is from that graph there. So I believe it. At this point, I'm going to turn the rest over to Laura, who's going to do the really heavy-duty work here, explaining how we collect our samples and what we're finding out.
All right. Can you hear me all right? All right. Yeah, so this is like, what, a relay race? We pass the baton, which is the clicker, to get into the next set of data. I'm getting into slides here, and I hope you all can stay jazzed and awake for the rest of this. We're going to get into some data now, and I know that that can get nitty-gritty, but I think you'll find it very interesting. So these are a set of pictures basically showing our sampling stations. Essentially, at each one of those stops that you saw on the map, we have something like this. So there's a little hut here beside the river. This is the Coldwater Creek station, actually. And in the river itself, there's a pump that's pumping water into that building, into essentially a sink. This is just a picture of a sink for our Rock Creek station. And then that sink of water flows through, and then it gets sampled using what we call an automated sampler. You can see that here. And then the samples are stored in a little mini refrigerator. It's like the little dorm refrigerators that you would go and see if you had, you know, when you're in college or had kids in college. And these samples are collected 3 times a day. We analyze all 3 samples if the water is muddy or turbid or if the flow is up. If not, we only do 1 a day, which only is really a caveat because that's still quite a lot of samples. And this runs all year round, 365 days a year. Every Monday, our technicians go around and pick up these samples. So if it's a Monday and it's raining really hard, or it's the middle of winter and it's a terrible snowstorm, please be thinking of our poor technicians driving all around Ohio trying to pick up some samples. We bring them into the lab, and we analyze these for all of our major nutrients and sediments. And these are pictures of some of our instruments that we use to analyze these nutrients. Today I'm going to talk about 3 different things. I'm going to be talking about 2 forms of phosphorus and 1 form of nitrogen. We're going to be talking about total phosphorus, which is denoted here. It's basically just the entire water sample. It has the particulates in it. It's got that muddy bits. It also is what's left over in the water. We can filter that and take all the particulates out, and then we'll have dissolved phosphorus. And I'll be showing you some data on dissolved phosphorus as well. And then I'm also going to show some information on nitrate, which is also what would be in the dissolved side. There's lots and lots of forms of nitrogen. I'm choosing nitrate because that's usually a pretty key indicator of agricultural land use. And then before I get into the data, I want to do, and this might be a little bit overboard, but I want to make sure we're all on the same page here. I'm just going to go over the types of things I'm going to present. So I tend to interchange these and then forget that maybe people aren't following me as well. So first I'm going to be showing you some data on load, which is essentially the mass of that nutrient as it enters into the lakes. This is really important for lakes. I'm going to show you concentrations, which is essentially that mass per unit volume. And then I'm going to show you discharge, which is essentially how much water is going by per unit time. So I'm going to put this into a scenario here. Now let's say I'm from Virginia originally, and we like our tea, our iced tea, with a lot of sugar in it. So if I have this iced tea here, and I add 3 cubes of sugar, then I'm going to have pretty sweet tea. That's a high concentration of sugar per amount of tea. But if it's too much, I could actually add the same amount to a much larger glass of tea. And it wouldn't be nearly as sweet, but in the end, it's the same amount of sugar, right? So this is our mass per volume. If we take out that amount of volume, we're going to have essentially that same mass. So that's how you can think of, if you have a really big river with a low concentration, it could have the same load as a small stream with a much higher concentration. And then the discharge would just be how many glasses of iced tea you drink in an hour. So if you drink a lot of it, then you might have a lot more sugar intake. Okay. So if we replace sugar with nitrogen or phosphorus, then that's how we're going to look at these data. Now the other thing I want to point out, so I pulled this map up just to show that some of our watersheds are huge. Muskingum is one of the biggest watersheds in the state. Maumee is very large, Great Miami is large, and then we have our little tiny creeks around here. So it's not really fair to compare loads across those without correcting for the size of the watershed. So I'm going to be showing some unit area loads, which is basically taking this load and dividing it by an area. The first thing I want to do here is just compare across all of our stations so you can see where our Grand Lake St. Mary's tributaries are comparing to the rest of these tributaries across the state. And I first want to point out, this is watershed land cover across all of our stations, and you can see agriculture's in yellow, urban's in red, and our forest is here in green. And what you'll first notice is the Cuyahoga River, we always like to compare to because it's urban. It's got a lot of point sources, so it's usually on one end of the spectrum. Most of our Lake Erie tributaries are pretty heavily agricultural. We have the Muskingum in here, which is mostly forest with a little bit of agriculture. And then we have these two Ohio river tributaries, the Great Miami and the Scioto, which are really mixed between both urban and agricultural land use. And then our Grand Lake St. Mary's tribs. For this purposes, I'm just going to be showing you Chickasaw and Coldwater because that's what we actually have full years of data on. Okay. So what do we see? I'm first starting off with what we're calling runoff. This is the same thing as discharge, but it's divided by that watershed area. So this is in units of centimeters. You can think of the centimeters of water running out of this watershed. And these are all in the same order here. What I really just want to point out is this is an average of runoff over the past 5 years. On the high end, we have the Cuyahoga River, which is that urban river. I think that it's particularly high in runoff because it's over in a different area of the state. It tends to just have high runoff. We have some lower watersheds here. These are up getting close to Michigan where the soils are really sandy, so they infiltrate water really well. And then right here, right in the middle, are the rest of our tribs, and that's exactly where Chickasaw and Coldwater come out. So I want to point these out just to show that in terms of water moving off the land, these Grand Lake St. Mary's tribs are very similar to what we would expect out of most of our tributaries and our sampling stations. Now this is showing total phosphorus. I have the dirty water here to remind you which one's which. Dissolved phosphorus here. And these are the unit area loads, and it's following that same scheme. So the Grand Lake St. Mary's tribs are here on the end. And you can note that both for total phosphorus and dissolved phosphorus, we are really seeing the highest unit area loads out of these two tribs. And compared to all those agricultural rivers that we are feeding into Lake Erie, and then our forested, the Cuyahoga, and the Raisin here are all basically making up the bottom end of our range. When we look at nitrate, we see exactly the same thing, except for maybe even more extreme. We're seeing a lot of nitrate coming out of these two tributaries. The next highest down here are really some of our Lake Erie agricultural watersheds that include the Portage, Maumee, Tiffin rivers, or not Tiffin, Honey and Sandusky River. So those are here, and then we have basically the same players are bringing up the lower end of our range. And I want to point this out because I think there's one of the really good things about our data is that we can get a good impression of where these nutrients are coming from. And one of the ways in which we can do that is by comparing what happens when we look at these concentrations during a storm. So if we see a concentration increase when flow goes up, that suggests that that water moved across the land and picked up some nutrients and they came in. If it doesn't, then, or if it gets being diluted with flow, then that suggests that normally there's a point source, there's a continuous input. So you can see this is Coldwater and Chickasaw, and both for all three nutrient types, we're definitely seeing an increase of flow. It's not nearly as clear for dissolved phosphorus. There's a little bit more of a shotgun effect here, but there's definitely an uptick under high flows. And just for comparison's sake, this is the Cuyahoga River DRP. Sorry for the color change. I pulled this from another talk and then I forgot to change the color. But you can see here a very clear decrease with the increasing flow. The Cuyahoga River definitely has point source inputs, so those point sources are being diluted instead of increasing with discharge. So this points to the fact that these three forms of nutrients are really coming from non-point sources. Okay, so now we're going to get into how much sugar is making it into the lake. So what are our trends in annual loads since we began measuring these? And this is really focusing only on Chickasaw Creek because that's the only place where we have multiple years worth of data. But I did pop in here, so these are all Chickasaw. This black one here is Coldwater for 2013, just so you have some comparison to see how these two creeks are comparing. And then what I've done is I'm showing you, this is discharge, total phosphorus, dissolved phosphorus, and nitrate. I'm showing you in green the spring loading, which is defined as March through June. And I picked that out because we're finding, at least in our Lake Erie tributaries, for those harmful algal blooms, that's the period of time that are the most important. So I thought that I'd at least start by looking at springtime loading here to see if that's most important as well. And then the total bar is the total annual load. So really, there's not a whole lot of pattern here, right? I mean, the external tributaries are bringing in nitrogen and phosphorus. They're bringing in discharge. These, if we look at this pattern and compare it to the rest, you can see 2011 is our highest year in terms of discharge, so we ended up having the highest loads, which makes sense when we're dealing with non-point source runoff. We do have some deviations, I'd say, once we get into these other years, and some of these nitrate loads are high regardless of how much discharge we're getting. But overall, one of the things I think is really interesting is that early on here, we're seeing that these spring loads are contributing a majority of the load coming in for the whole year. So we're talking about 4 months here bringing in pretty much everything that's getting into the lake. And then you hit 2012, which was a drought year, particularly in the spring and the summer. And I should have mentioned that these years I'm talking about are what we call water years. And we do our water years from October of the year before. So this would, for 2012 would have been October of 2011 to October of 2012. And we do that because we go from essentially a dry period to another dry period. And so you can see that 2012, very little of the load was contributed in the spring. So if we had a low algal bloom year then that would be a good reason as to why. Since then, I would say in 2013, depending on what you were looking at, about half the load came in the spring. And so far, I had this sort of grayed out because we're not done with 2014 yet. But it looks like we're getting a good amount of load, but maybe not as much as what we've gotten so far. It depends on how much it rains over the next month or so as to what these spring bars are really going to end up being. And in general, if we compare 2013 years here, we can see that Coldwater is not all that different from Chickasaw. Maybe a little bit lower, because it's probably a little bit smaller stream, but they're very similar. Okay. Does that all make sense? We're all good? Still awake? Woo! Okay. All right, so what I wanted to do was to show you sort of an update in the data as it's going. I want to be able to do this for you as we're getting data in. And so I want to calculate what we call the cumulative loads. So I'm going to step through this real quick. This is the dissolved phosphorus loading rate. So this is that mass coming in per day instead of over a year. So it's just still how much sugar is getting there, but now it's, we drink it in a day instead. And you can see how storms end up bringing a lot of the load. Because not only do we see an increase in concentration, we also see an increase in discharge. So we kind of get a double whammy here. But what we can do is take this and we can start adding up all the days over time. And when we do that, so that's the cumulative load is the sum of that daily loading, you get something that looks like this. So essentially as we go over, as we add these days up, they go up, right? And then this would be our spring loading number here. And you see these stair steps here when we have really high loading events. You can see how much of an influence on the load one rain event can really have. And that really also shows us that this is non-point source runoff, because if it was point source, it would be about the same every day, it'd be a straight line, right? But if we see this, what I call a stair stepping up, that's really an indicator of runoff. Okay, so I calculated these cumulative loads for all of our metrics for all the years that we have for Chickasaw Creek. And starting with discharge here, you can see we're going from March to the end of June. And you can see all of our years. In green, I have 2011, because that was a particularly high year. And blue I have 2012 because that was a particularly low year in terms of spring loading. And then basically you see these two make the upper ends, and we have everything else is sort of in the middle. What I think is interesting is some years we get some big rain events here in April that really bump up. This is what happened in 2013. Sometimes we get them earlier on. And in 2014, we did have an early April rainstorm that seems to be contributing a lot to the amount of water that's making it to the lake. So how does this compare to what we see when we get onto loads and bringing in our nitrogen and phosphorus? Well, for total phosphorus, really it follows discharge very well. And 2012 or 2011 is very high, 2012 is still very low, and I think we have the exact same pattern here right in the middle. 2014, if we got no more rain, is coming out for total phosphorus a little bit lower. If we got more rain, you know, it could bump up to anywhere in this range. So the very minimum is we're still going to be higher than 2012. For dissolved phosphorus, we're tracking right in the middle. So here we've had some swapping of what years were most important in terms of dissolved phosphorus. You can see 2010 now pops up as being a pretty high year, still lower than 2011. And 2014 is really tracking right in the middle of somewhere between 2009 and 2013. For nitrate, again, we've seen a big swap. 2010, our nitrate runoff was almost the same as 2011, even though we got so much more discharge in 2011, which is, I think, really interesting. 2014 looks like it's coming off somewhere on the low end. It depends on what happens again over the next month or so. And then to start wrapping this up, I wanted to show what we are finding so far in the 2014 water year. And in particular, I want to show what Beaver Creek is looking like, because I think this is also pretty intriguing. So this is showing October through June. So I got all the way up to June 1st for our data here, which is really something because that means our technicians analyzed all those data and got it to me like very, very fast. This is total phosphorus, dissolved phosphorus, and nitrate. And then the blue in the background is discharge for Chickasaw Creek, just so that you have some comparison to see where the storms are. And you see what you would expect, you know. We see increases in concentrations of storm events. We see some increases sometimes in the late summer. And what's interesting here is that for total phosphorus, really what's coming out of Beaver Creek and what's going into the lake from these two tributaries, in terms of concentration, are very similar. Except for you just don't see the flashiness in Beaver Creek. When we look at dissolved reactive phosphorus, though, you can see that the concentrations coming out of the lake are minuscule compared to what's coming into the lake. So we have a lot coming in and very little coming out. And then that's the same with nitrate. What's interesting about nitrate is the concentrations are quite high, and sometimes we get dilution with storms instead of increases, but that has to do with a lot of details that I could tell you about if you're really interested. Okay, so why is this happening? And I popped up this figure here. This is showing a Chickasaw Creek sample from last Monday and our Beaver Creek sample from last Monday, and you can see that indeed the lake is retaining a lot of these nutrients, likely because there's a lot of algae growing there. But what I didn't put up here, and then in terms of the processing, is also that, you know, if the wetlands that have been put in place and future wetlands, they would also lead to these decreases as well. And then this is all MAMI data, and I just wanted to point out that indeed these concentrations that we're seeing are quite higher than what we see in the MAMI. Now the MAMI is a lot larger river, so we would expect it to not be as spiky, not as flashy, because it takes, you know, a long time for that, you know, those samples to kind of move through that watershed. So in some ways it's not a completely fair comparison, but in other ways I think it is. And we look at dissolved phosphorus and we see how very low it is in the MAMI, even though the MAMI is causing all these problems in western Lake Erie Basin.
Oh, I wrote my battery.
Okay. And the last figure that you can't see right now, though, is also nitrate concentrations are substantially lower in the MAMI River compared to what we're seeing here. So there's definitely, besides just these loads coming in, you can just see it in the concentration, even if we don't take into account discharge or this period of time. Well, I'm trying to remember what my next slide was going to be after that. I think that was almost it, really. So it's a bit unfortunate that you don't get to see whatever is coming up next. It's probably just going to be some more pictures. But that's all right. But if we start to summarize what we're showing you here, the first thing that we're seeing is that we are seeing some pretty high loads coming from these external tributaries. And interestingly, again, the lake does seem to be processing a lot of these loads, so it's not making it all the way to the Wabash and down to the Ohio River and contributing as much to the Gulf of Mexico, but it is contributing substantially to the types of blooms that you're seeing in the lake. The other thing I showed is that these sources appear to be non-point sources, which I think has been pretty well established for this watershed, but I wanted to show you how our data can inform that type of information. And what was the next summary point? I think then we can get into thinking about these cumulative loads. So 2014, so far in terms of the spring loading, doesn't seem to be as high as when we had the earlier monitoring, right? So and that would imply that maybe we should be seeing less of a bloom this year if spring is important compared to other years. But that might not be the case. My understanding is that there is some green, some blooms already starting to happen in the lake. They're just not as bad as it has been before. If that's the case, then what we can say, is that maybe there's other things besides just external loads that are contributing to these factors. And it seems to me that, with these inputs coming in, that treating these tributaries before they get to the lake, as was discussed earlier, seems to be probably a pretty good line of action. It's probably the best hope that we've got so far. And once this comes up, we'll put it on my conclusion slide, which has the link to our website, my contact information if you have any questions, and it'll have a link to a Facebook page. I don't know, is it ever coming back? Okay. Well, then it's not going to come back, but you can follow me on all of those ideas. I do think we have made it to the end of the figures, so we're totally fine.
I'll have some business cards up here that we could...
Yeah, we'll have business cards, and I'm sure I could open it up on my computer if you guys want to see. So I think that's all I have. If there are any questions, I hope you don't want to go back and see any figures. So, yeah, so we can open it up to questions.
Okay. I have a quick one.
Sure.
You lost the slide on the beaver, but you showed in the streams it's very spiky in the concentrations.
Yes.
Okay, in the beaver flowing out, does it show that, or does it pretty much level in the concentration?
It levels it.
Yeah.
So even with, say, total phosphorus, where it is very spiky going in, the concentrations are not very different because, total phosphorus is both what's dissolved and what's particulate. And what you didn't notice in that slide is that most of what's coming in is actually dissolved, but probably most of what's coming out is more particulate because there are actual, bacteria and algal cells or even sediment that's, potentially even holding some of that phosphorus. So, so it basically evens it out. As you can imagine, if you had something spiky going in and then you have this big lake to take it and sort of smooth it over and then send it out. Okay.
Yeah. Do you have an idea how much of the nutrient loads do the partially applied manure each year versus residual soil?
Yeah, so the question, if you guys couldn't hear, was how much of the nutrient loads are from fresh versus, say, the old residual manure that's been applied to these fields. And I guess the answer really is that we can't completely tell. I mean, we can speculate based off of, how much runoff we get given a storm event if we know when applications are occurring. But using these type of data, it's very difficult to discern and separate out oftentimes what is been recently applied versus what is the legacy stuff that's basically continuing to leak out. One of the slides that I have towards the end would have shown that our soil test levels, at least for phosphorus in this region, are very high. So there's a high potential for this continual legacy phosphorus leaking that's going to probably continue to plague the external nutrient inputs for some time.
Would alum help on that?
Would alum help on that?
How do you deal with the legacy? Assuming you stop the excess nutrients going on, how do you deal with the legacy?
And that's where it gets very complicated indeed. I mean, alum would help with whatever is in the system itself, but if we're having this continuous input, that's where I think that trying to deal with the tributary inputs themselves is probably the best way to go. Talking about doing something like treatment wetlands or something treating the tributaries before they make it to the lake. If you do that and you can reduce what's getting to the lake, then I think something like alum would then be very successful because there won't be this continual input continue to feed the bloom. Maybe I should switch to that. Is this one still on? Okay. Sorry, we're getting some weird feedback. I don't want to. Were there any other questions though? Now that I switched over. Yeah.
Well, with the no-till type of truck this time,
Would no-till help with this?
with the weather events, where you go out and rain?
It's complicated, as you might imagine. We think that if we had a true no-till and people were doing some progressive things such as using cover crops so they don't have to apply as much fertilizer, and if that increases things like water infiltrating into the soil instead of running off the surface and that sort of phenomenon, if all of those things happen, then we think that it would help. But the problem is that it takes time for all of that to occur. So people would have to be patient. If we're going to promote something like no-till and something like cover crops with that, we have to say, all right, well, it's going to take some time for the organic matter to build up and for these to have some effect. So, you can't just do it, one rotation or even just for your 3 rotations and see effect. You should really think about this in terms of a long-term treatment. What I think would help the most is thinking about how and when and how much fertilizer is being applied or manure is being applied. Yeah.
Just one last, the funding ends in 2015. You see this continuing on now?
Yeah, I believe so. We anticipate that the results are going to be intriguing enough that the current funders are going to want to continue, we hope. And if not, we'll probably go around and seek out continued funding from other organizations. And we've had to do that with some of our other stations in the past and have been relatively successful at it. It takes a lot of work to continually chase funding like that, but we think that the data are all very much worth it.
Are you able to distinguish the source of the phosphorus coming from the soil or from commercial fertilizers versus what's coming from manure?
We can't do that necessarily in our data. I think people have been able to do that in the past, but in reality, well, with nitrogen you can do it pretty easily because you can track different signals associated with nitrogen to do that. But in reality, when you look at something like a manure input and a commercial, something, if you're broadcasting, say, fertilizer on the top, it functionally is not all that much different, I don't think. We could possibly look at other forms of phosphorus besides dissolved phosphorus, like organic phosphorus, which we've never found to be very high concentrations, but it might be worthwhile to do a double check for these particular data. So that's a good idea. We should look into that some more.
Would you be in favor of banning phosphorus? Because from what I understand, like corn, that's, if you're putting commercial fertilizer on that, versus just dry phosphorus.
To me, now this is probably not necessarily what everyone's going to say, but I think banding would be a great idea. To me, I'm thinking, if we're banding along a row, then it's going to be a substantially smaller amount of area compared to broadcasting on the entire field. But that does require some precision farming techniques, and if we have big commercial farms, sometimes timing is just not really appropriate for that. So I think that makes sense. I think injecting, if you can inject into the soil instead of just having it sit on the surface, should also help as well. And we've had some work from our watershed modeler that's indicated for at least commercial fertilizers, not manure, those sorts of practices do help. Now, those are all a part of the 4R nutrient strategy that's sort of been making its way through, which is applying fertilizer at the right amount, with using the right source at the right time and at the right rate. It's 4 things. And so basically it's saying, well, we need to look at how much phosphorus is in our soil, think about when we're applying it, making sure it's not right before a rain event or on frozen ground, which is not really allowed around here anyway, and just making sure that it's right where the crops are going to need it as much as you can possibly do. So. Anybody else? Okay. I think that must be done.